Let's try to conclude the renewable energy part in the adaptation with this report from IRENA again, the International Renewable Energy Agency, which is under the UN. And they have this report called Advanced Forecasting of Variable Renewable Power Generation, VRE. And the innovation landscape is what they are trying to discuss here. The tagline, of course, is Advanced Forecasting of Variable Renewable Power Generation. Improved weather forecasts allow accurate estimates of the amount of solar and wind electricity likely to be available in specific time frames. I see this as part of the adaptation as well in terms of early warnings for managing renewable energy, which is obviously always intermittent and variable because you don't have sun all the time, you don't have winds all the time. And that's part of the adaptation as well in terms of managing energies for variable weather and climate in the end. What's advanced generation forecasting? Meteorological technology captures real-time site-specific weather data. Algorithms produce advanced forecasts for solar and wind output. I won't go into the details here and just stick to this report because I have a whole course on subseasonal to seasonal forecasts where we discussed various points about forecasting for various sectors, including a little bit about energy. But there is a lot of literature on this if you want to follow up. What are the benefits? Accurate generation forecast for solar accurate generation forecast for solar and wind power, short-term and long-term, centralized and decentralized, are valuable to system operators and renewable generators. I'm fumbling the words a little bit. I just had lunch, so maybe I ate too much. Electricity trading in spot markets, so generator benefits and system operator benefits include these kind of things. And renewables point placement, system stability and system planning, short-term forecasting to long-term forecasting. You go from there to there. Okay, those are the benefits. Key enabling factors, which we will come back and look at just a little bit, just like this. Regulatory incentives for accurate variable renewable energy forecasting, open source systems for weather data collection and sharing, advanced meteorological devices. So now you have in situ observations in the ocean, in the atmosphere, on land. You have drones, you have satellites, you have other unmanned vehicles, robots, all sorts of things. And there is a strong wind here perturbing my, so I didn't plan for the wind. So let me go ahead and shut the window. So even though I don't have hourly wind forecast for my apartment, I know by observations that there is a strong diurnal cycle in the wind, especially when it's not raining. So today we are in the middle of monsoon, July 31st, and it's not raining today. So as soon as afternoon arrives, the winds pick up, which I should know and plan for. Anyway, snapshot: Australia invests US $5.6 million in advanced wind and solar forecasting to improve decisions made on spot markets. That's an economic term that you can go and learn about. It basically where people are doing kind of instant trading of electricity, buying and selling. The UK system operator uses artificial intelligence to better predict renewable energy generation. Very briefly, all the weather forecasts happen at some kilometer scale, like 10 kilometers, 12 kilometers, 30 kilometers and so on. And pretty much necessary now is to take data and reduce those forecasts at tens of kilometer scales to local grid scales or solar farm scale, wind farm scale by using artificial intelligence. So artificial intelligence in that sense is now an indispensable, unavoidable part of any forecasting and applications of forecasts. to energy, for example. A study from the California Energy Commission indicates potential savings of US $2 million yearly with improved solar and load forecasting. So the skill is not always good, but decisions are made nonetheless, and empirically you do forecasts and you learn the bias in the model, you correct the bias. So there are various approaches. There's another IRENA a report which looked at innovation dimensions for renewable energies. So there are enabling technologies, business models, market design, and system operation dimensions where innovation can happen. So here, of course, you have utility scale batteries, behind the meter batteries, electric vehicles, smart charging, renewable power to heat, renewable power to hydrogen, Internet of Things, IoT, artificial intelligence and big data, blockchain, renewable mini grids and super grids, flexibility in conventional power plants. And in business models, you have aggregators of people who buy and then retail, peer-to-peer electricity trading, energy as a service, community ownership models, pay-as-you-go models. These are all business models for energy. Market design, increasing time granularity in electricity markets. So the better the forecast, better you are able to hedge your bets on minute-to-minute time scale. Maybe increasing space granularity in electricity markets in terms of how demands are distributed, commercial spaces, office spaces, industries, domestic spaces, and so on. Innovative ancillary services, redesigning capacity markets, regional markets, time of use tariffs. So if people are charging their vehicles, there is always a concern that they will charge at any time of the day and they will negatively affect the utility rates for everybody. But it turns out that that doesn't necessarily happen. I have podcasts elsewhere on that based on data from California. But time of use tariffs are possible so that you charge your car at a time when it's a non-peak hour and so on. Market integration of distributed energy sources, net billing schemes, and so on. System operations innovations include future role of distribution system operators, cooperation between transmission and distribution system operators, advanced forecasting of variable renewable power generation, innovative operation of pumped hydropower storage. So that's a storage to manage intermittency, virtual power lines, and dynamic line rating. I'm not defining all the terms, but you can go and read them up. Weather and power generation forecast, you have weather forecast and plant availability combining to give you power generation forecasts, and generation forecast methods and applications. I won't go into terrible details here because this is quite generic, and we have discussed this in much more detail in the S2S forecasting. So power generation forecast, 5 to 60 minutes, 1 to 6 hours, days ahead, weeks, seasonal, a year ahead. Skill differs based on which time horizon you're looking at. Methods can be statistical, persistence, the blend of statistical and numerical weather models. The AI comes in here as well. NWP is numerical weather prediction with corrections of systematic biases that I mentioned. For example, the forecast from the India Meteorological Department for Mumbai tends to be shifted by a day for heavy rainfalls, but once you have enough samples of this data and the forecast, you can adjust this empirically. Climatological forecasts and numerical weather predictions, so you know climatologically what to expect on July 31st in this region of Mumbai, and then you look at current day's weather and you adjust and produce post-processed information. Key applications include regulation, real-time dispatch, that's energy, trading, market clearing, scheduling, load following, congestion management, scheduling, reserve requirement, for these are different time scales. Resource investment planning, contingency analysis, maintenance planning, operational management, and so on and so forth. So from weather to power generation forecast, you have NWPs, numerical weather forecast models. Weather forecast models give you temperature, solar irradiance, wind, wind velocity, humidity, rain, etc., which feed into energy forecast models, and that goes to generation forecast. These get feedbacks also, input also from plant characteristics and plant availability. Of course, weather forecast models ingest public weather data, private weather data, public sensor data, etc. Contribution to power sector transformation, we already looked at it a little bit. Benefits of weather forecasting to system operators and renewable generators. Benefit of weather forecasting from short and long-term forecasting to centralized and decentralized forecasting for system operators and renewable generators. So you have multiple axes being considered. At the short term, you have improved network management and system balancing, advantages for intraday and day-ahead electricity market trading, reserve planning and operation management for long-term forecasting, as well as planning for extreme weather events. And for renewable operators, you have efficient placement of renewable plants with this kind of long-term forecast information. Potential impact on power sector transformation. So several studies have explored the impact and implications of advanced forecasting for utilities, system operators, and variable renewable energy generators. So there are studies which looked at impact of improvement in solar power forecasting. The study showed that the electricity generation from conventional sources such as gas and oil generators decreases with solar power forecasting improvement. So you have an advantage of improving solar power generation with forecasts and reducing reliance on fossil fuel power generation. Day-ahead operation can be better planned, and faster generators committed in real time can be used less when solar power uncertainty decreases. So reducing intermittency has direct impact on coal, oil, gas, and so on. Impact of solar power forecasting improvement on power generation. So here is forecast improvement. I won't go into the details, but you are looking at solar penetration in terms of the percentage of people or energy being supplied from solar, coal change, gas and oil. So this is combined cycle, steam engine, gas and oil turbine, and internal combustion. So you can see that various reductions in reliance on coal, which is not much here. Actually, they're all positive numbers. So you can actually interpret these based on whether there is a move to reducing the use of fossil fuel or actually increasing the fossil fuel use, and so on. So you can see that higher the reliance on solar penetration, higher the impact on percentage change in coal based on improvement in forecasts. Okay. Study shows also considerable decrease in solar power curtailment with improved forecast. Again, not going into detail. So impact of solar power forecasting improvement on solar power curtailment. Generally, idea is that solar power forecasting improvements give you better handle on lower operational costs for the system, okay, which is shown here. I won't go through the numbers because we are not paying attention to the details of how these things are done. The main message you want to take is that improved forecasting for renewables will help you manage intermittency better and improve solar production, renewable energy production, and cut down your reliance on fossil fuel. Total cost savings from improved wind power forecasting. Wind scenarios are considered, forecast improvements are considered, annual savings are considered, and some of these numbers are fairly massive. This is a $146 million saving annually if there is a 50% in uniform improvement in forecast with wind scenario at high. So if you have a high wind contribution to your portfolio and you have 50% improvements in your forecast, then you have up to $146 million saving potential. Is it realized? Will it be realized? When will it be realized? Where will it be realized? Of course, have a long way to go. These are scenarios. We looked at the benefits before, key factors to enable deployment, a regulatory environment incentives, incentivizing accurate variable renewable energy power generation forecasting is an enabling factor, open source systems for weather collecting and sharing, advanced meteorological devices. These are not just for renewable energy, but these are also good for application of weather forecasts and short, medium, and extended range forecasts to food, water, energy, health, transportation, and many other sectors. Current context and ongoing initiatives, short-term VRE generation forecasting solutions in Australia, Sun4 forecast solar generation forecasting system in the United States, and various other projects improving VRE generation forecasts in Germany, hybrid renewable energy forecasting for advanced wind forecasting in China, and there is a list of implementation requirements and checklists. Maybe I should come back and read this in the next podcast, since this is already about 15-16 minutes long. I'm reading them off fast, but the report is only about 22 pages long, so, and it has a lot of citations, so if you want to get more details, you can obviously go back and read the report, and I'm just giving you brief introduction to the topics so that you can get started. Okay.